Hi everyone, my name is Erik and I will be introducing the concept of an inexact loop. The primary goal of this work is to build towards a formal definition for what is meant by a loop in the context of a loop closure within SLAM problems. Along the way, we will find that such a definition generalizes to other robotics problems as well. Trajectories are ubiquitous in robotics, and loops are a fundamental concept in the study of trajectories. Loops appear within SLAM, where we want to identify loop closures to improve our reconstructions. Within homotopy-based path planning methods, where we're interested in whether two trajectories are similar. And within exploration and optimal path coverage problems, where we want to plan paths that minimally revisit previously seen locations. It's uncommon in these applications to encounter a real loop, whose start and endpoints are exactly equivalent. Here's an example of a trajectory driving through a cul-de-sac, which has no loops on it, but comes close to itself. If we zoom out and look at this particular trajectory, we see that it never crosses itself or forms an exact loop. But every point on the trajectory is close to at least some others that were far apart in time. It's easy to find pairs of points on the trajectory that are nearby one another that we could consider to be the same place. But it's hard to reason about these in discrete terms. Should we consider this example one loop closure, or is it really many? Loosely speaking, how big is this loop? And what is this segment's loop density? These details become extremely important when our problems become large. Here's a 100 square kilometer cutout patch of map consisting of approximately 800 hours of driving data. This reconstructed factor graph has about 4 million nodes and therefore entertains a possible 16 trillion potential loop closure constraints that could be generated. Which ones should be considered and which ones can we safely omit? To explore this problem, we consider trajectories embedding a time interval into an arbitrary smooth manifold. An exact loop is a trajectory whose start and endpoints are identical, while an inexact loop simply allows for some distance between these endpoints. Continuously moving the endpoints of an inexact loop produces other similar inexact loops. If we consider fixing a particular trajectory, xi, we can examine the inexact loops on it, such as this blue one here. For L to be considered an inexact loop, its endpoints must be near one another, which just means that under a given distance metric on this manifold, if we evaluate both endpoints, we are returned with a distance value that falls below a threshold value. This type of metric is general and can potentially describe distances between sensor measurements captured from two locations, or it could just be a simple metric such as the length of a geodesic on the manifold. Using this type of metric, we can evaluate the distances between all pairs of points on the trajectory, producing a 2D plot as shown on the right here. Sublevel sets within this plot correspond to clusters of inexact loops on the trajectory, which we call loop components. Loop components give us a formal way to group or cluster areas that have loops. They also give us a way to speak about how large a particular loop is, since these components have measurable areas. For trajectories that have no exact loops at all, we still find interesting patterns in their sets of inexact loops. Our definition also extends to curved manifolds. Here are two circles embedded into a torus and into the group of rotations SO3, whose sets of inexact loops have very different structures. On real trajectories, we see that the areas of loop components are important when sampling loop closure constraints for SLAM. Our definition lets us build several loop-related properties that can be measured on a trajectory. Loop duration measures how often a point is a member of an inexact loop. Loop area measures how often a segment is a member of an inexact loop, and loop density measures how many inexact loops are connected to the average point. Our definition additionally allows us to characterize the possible complexity classes of discrete loop sampling algorithms, such as those developed in existing SLAM approaches. We experiment with using algorithms from these complexity classes to sample inexact loops on real trajectories, finding that existing loop closing approaches pictured on the right in pink tend to oversample large inexact loop components and undersample or miss loop closures in small loop components compared to algorithms that consider loop area. For more information, I invite you to read the paper, and thank you very much for watching.